Hello, everyone, and Robert, thank you for that introduction. Again, I'm John Baldiga here with Mike Webb, and we are going to be going over Intelligent Interference Check, or more commonly referred to as IIC. So let's just go ahead and jump in and get started here. We have our agenda. We're going to go over what it is, the requirements and the limitations, some of the foundations, a quick example, talk about the protocols of communication for IIC. We'll go through the functions that you can use. Then we'll wrap it up with the conclusion and questions and answers. I'd like to start out by saying, by noting that the IIC manual that you'll be using is Basic Interference Check and Intelligent Interference Check, which can sometimes be confusing when you're looking at an alphabetical list for Intelligent Interference Check. Just want to point that out. So what is IIC? In a nutshell, Intelligent Interference Check is a software option that really gives the robot a way to monitor its position and its environment around it, so the robot can proactively prevent a collision from occurring. We have a video here. Okay, well, I hope everyone is excited about IIC after that video. More on what IIC is. It's really all of the features of Basic Interference Check, arm to fixture detection, critical zones, 3D visualization, and space check, plus arm to arm detection with single or multiple controllers, a deadlock prevention function, and real zone interference check. So here is the product description page, which is available on the Customer Resource Center. Any information that you have or any questions that you have about this option, or if you'd like more information about this or other options, the CRC is a great resource to do some research to find out what we have available. Going into the requirements and limitations of Intelligent Interference Check. Robot requirements are software version 8.10 or greater, 64 megabytes FROM DRAM, which shouldn't really be a problem because that's standard on our units now. Additional limitations, multiple robots will require an Ethernet connection. The protocol there is RIPE, and that's packaged with Intelligent Interference Check. The 4D graphics option is highly recommended. We could not recommend it more. It allows you to visualize your models that you build for your application, and that visualization really saves a lot of time and makes troubleshooting and setup so much easier. Another thing I want to note about memory is IIC is considered one of the bigger software options. So if you're combining it with another big software option such as IR Vision or LVC, you may want to consider upgrading your memory. So getting into the foundations of how IIC works. Well, by default, the robot comes loaded with a virtual safe zone around it. So on the left, we have the standard robot. On the right, IIC, much like our DCS, puts a zone around the robot. And these zones are referred to as models. So the robot model is provided. And then it's up to you to create the safe zone around the tooling, which is called a hand model. And these are made up of elements. So as you can see the difference in the photos here, the robot on the right has the safe zone around the tool, and it's made up of 3 separate elements, which are 2 cylinders and a sphere. The other type of model and the other setup task is to set up the safe zones in the robot's work envelope, its operating environment. These are referred to as fixture models, and they're also made up of elements. So say we wanted to protect this table, we could build a safe zone around it, a box fixture model. The available elements: a sphere, which is a point in space with a radius; a cylinder, which is 2 points in space with a radius. I should note now that the cylinder and the sphere are the only 2 available when teaching a hand model. When you are setting up a hand model, the only 2 elements you have at your disposal are a sphere and a radius. Or, I'm sorry, a sphere and a cylinder. We have a finite, infinite plane, or a finite plane. And then we have the box. I'm going to run through here and show you guys a quick example of setting up a hand model. So here we have our cell. This is robot 1. It already has a hand model. I'm going to set up the hand model on this other robot, which is there's a camera, a horizontal gripper, and then the large gripper. So I'm going to pull up the Teach pendant, and this is where 4D graphics really comes in handy. Got double screen, intelligent interference check display. We'll zoom out a little bit. Now on the left, I'm going to open the interference check setup menu. Menu setup interference. We'll go into model setup, detail, press enter. Hand models setup. I'm going to go ahead and give this a name, press enter, and using the keyboard, we'll just call it end of arm tool. Now, I'm going to press, at this time I'm going to press F4, which is utool data, and that is what sets my model active. If utool 1 is active, then model 1 is active. So here are all the elements I can use to build a tool. I want to build an element on this camera thing here, and I'm going to make a sphere. No, I'm sorry, I'm going to make a cylinder that's going to encompass that camera holder. Set the size to 125, the X to 40, Y to negative 235, Z to 45, X to negative 80, Y negative 235, and Z 45. Now, I just want to go ahead and say that, disclose this, that I've already done these measurements, and I know that, that putting these values in will put my hand model exactly where I want it. So now I'm not going to see it update in the 4D graphics window until I enable it in the setup. So I'll go ahead and enable it. And sure enough, there it is. I've got position 1 and position 2 with the size that is the radius of that cylinder. So now I'm going to go back into the setup, and I'm going to set up a cylinder for this for the horizontal gripper sticking off to the left. This one I'm going to set up a cylinder again. The size I'm going to set to 75 millimeters. X is going to be 0, Y 250, Z 75. For the second position, again, X 0, Y 0, and Z of 75. So that's going to be X, it's coming directly out of the plate. Y, it's going to the left 250 millimeters, so around where the pointer is. And then Z is 75 millimeters straight down. Now position 2, 0x, 0y, and just Z 75. So position 1 is over here. Position 2 is over here. I'll go ahead and enable that. And here you can see it in the IIC window. Position 1, position 2. And it created that cylinder. Now for the third one, I'm actually going to create a sphere. And the sphere is going to encompass this entire area of the, say, the large gripper that's facing down at the moment. So this sphere is going to encompass this gripper. I'll set the size to 150 millimeters and the Z value of the position to 175 millimeters. That's basically 175 millimeters from the faceplate. Press apply, and the view updates in the 4D graphics editor, and I think I have my hand model taught. Now at this point I'm kind of cheating a little bit because I already have this set up in a DCS user model. So if I make that visible, these are the same values that I just typed into the teach pen. If I make that visible, then I can get a visualization with the tooling CAD to absolutely to confirm that I am covered by the hand model. And it appears that everything's covered there. It doesn't look like anything's sticking out. So that's that was a quick example of how to use the modeling function to make your own models. Now I'm going to get into the communication protocols required for IIC. These basically allow multiple robots to do position check, arm-to-arm interference check. So RIPE and MASH. RIPE is the ROS interface package over Ethernet. It is a high-speed communication protocol, and again, it is included with IIC when you order the package. Next, we have MASH. No, it's not the old television show. It is Multiple Arm Sync Handler. is really just a just sort of like a listing of the arms for synchronization purposes. So going into that, I'm not going to set it up on this cell because it's in RoboGuide and it is it's not true to life. So, but I'm going to show you guys where it is and what the menu items are. So, okay, give me a moment here. We have a question.
Yeah, the question is what does it mean by the hand model? That's the end of
the hand model is yeah, it's the safety bubble around the robot's hand, the safety bubble around the tool. So you're designing your own model to encompass the tool, so that way it's protected before the tool hits something. So the robot's model is the green portion, and the hand model is the blue portion. Because pretty much every the robot that you get, the robot knows what type of robot it is, so it's going to pull in its own model. But the end effector could be different. It's going to be you're going to need to customize it almost every time. Okay. Okay. Yeah, Mike was just saying that the robot models, which I'm not going to cover, that I wasn't planning on covering in this webinar, you actually have the option to add additional features to the robot model, such as dress pack and stuff like that. Okay, so continuing on with RIPE and MASH, I'll show you where they're located. So the RIPE setup protocol, let me backtrack this video a bit. The RIPE setup protocol is in Menu, Setup, HostCom, and in the protocols list you'll see RIPE. Go ahead and select that and press Enter. Now here we have the host name, the port number, the Ethernet, the IP address, the number of members, you have an update interval, and then you have basically a list of all of the hosts. The function keys we have down here, we can load or save RIPE data. We can also set master, slave, and auto setup. Now getting into the multi-arm setup, really it's a listing of the arms with a host name and group number configuration. So you're really setting up who is in this multi-arm configuration and what is their host name for communication purposes. All right, we've gone through the preliminaries. Now let's have a look at what IIC has to offer and go into some of the functions required to get it functioning. I'd like to start off by going through the setup menu list. A lot of times it helps to go through each item in a setup list, so that way, well, so you know what they do. So I'm going to start with calibration between robot, and I want to note now that item number 4, which is check data setup, I'm not going to cover that because really that's more of a that more contains factory set values, and you should only really adjust those if you're having troubles. But we don't typically adjust those. So I'm going to start off with calibration between the robots. This is really how the robots get an idea of where the other robot is in three-dimensional space, so that when they're about to hit each other, they know they're about to hit each other. So for the robot calibration, we specify a manager. Well, let me backtrack a little. This is done in menu, setup, interference. Again, there's our menu, calibration between robots. We're going to specify the manager of the calibration, a member, and then the other member. Now, I should note now that I'm assigning the manager to be robot number 1. But robot 1 is also a member of the group. So the other member of the group is robot 2. So robot 1 has the role of manager and member 1, or I should say, and member 2. And robot 2 over here has the role of member 3, robot 2. Now I'll press, pardon me. Back into calibration again, robot 1 manager. Robot 1 is also a member, and robot 2 is also a member. Now when I press F3, which is calibrate, by default it takes me to the direct entry method for calibrating these robots. But if I press method, I also have 3-point. There's a reference robot column, and there's a cal robot column. Now in the next slide, I'm going to walk you through the methods for calibrating the robot. We have 3-point calibration across the controllers. You'll jog the robots to the point where their TCPs touch. You'll record calibration point on the reference robot and calibration point on the calibration robot. And you'll do that 3 times in 3 different positions. The other method is the direct entry method, which was the default setting. If you know where the robots are relative in 3D space, because you have a detailed engineering drawing, you can actually go ahead and just plug in the values of how far away the robots are from each other. And the other method, which is my preferred method, is 3-point calibration across controllers using a common reference. So the corners of this table, for instance, are points 1, 2, and 3. And then on the other robot, you will touch those same corners, 1, 2, and 3. And once you do that, they've developed they're able to calculate their relationship to one another, and calibration is complete. Next, we're going to go into model setup. I already covered the hand model, which was the end of arm tooling. So I'm just going to go into an example of a fixture model. Again, we'll go to menu, setup, interference, go into model setup, fixture models setup. Now I have one predefined here for the machine door. I have it set up as an infinite plane. As you can see, I have 2 elements. One is enabled, one is disabled. And here are the settings for that infinite plane. It's enabled, it's an infinite plane. Then I have 3 positions taught, which generate that plane. The 4th is all zeros because it's not needed. I'll press, I'll go into my 4D graphics, and this is what the infinite plane looks like. You can see that it's right where it needs to be to prevent the robot from bumping into the machine. But with this setup, I'm not able to go through the door. So I'll just show you here that I have a space check alarm because I just jogged the robot into that fixture that I created. Space check, group 1 is near to target. I'll go ahead and jog it back away. So that's sort of how the fixture works. You assign a space, and well, first you assign a space. What you do next is a check combination setup. Because just because we defined the models, just because we defined that there's a wall here or there's a box here or a sphere here, it doesn't necessarily mean it's going to work just yet. We need to use combination check to tell the system that this model is not allowed to touch this model, or this model needs to wait for this fixture model. So going into our next video here, I'm going to show you how to set up the check combination for this wall. So one thing I might add about the check combination setup is that the wall that we have defined for this machine, well, it doesn't make sense for this robot over here to check for it, obviously, because it can't reach. So in the combination to check menu, I have robot RH1, which stands for robot plus hand, group 1, is checking fixture 1, which fixture 1 is the one that we specify is the fixture, the infinite plane that we just saw, and the host name is robot 1. We also have details. We have a digital input for disable. This is basically an input that will tell the robot to disregard this. I have this set to digital input 8, and digital input 8 is my signal that the door is open. I have this interconnected to my digital output 8. So when I turn on digital output 8, digital input 8 comes on also. So when the door is open, DI8 is on, and this space check is disabled. This combination check is disabled. Now, if I want to do robot to robot checking, I will I'm going to set up this the second. Give me a moment here. I'm going to set up this second combination check item to be robot 1 and robot 2 to make sure that they don't collide. So here I have robot plus hand, but these are all of the options that I can put in my combination check. I can do robot plus hand, I can do a fixture, a critical zone, a virtual fence, DO only, or PLC DIN. But for this, I'm going to do robot plus hand. Basically, this combination check is robot plus hand is looking at robot plus hand, and the host is going to be robot 2. Again, robot hand 1, choice robot 2. And we'll cycle power on the robot. Then once that robot is back up, you can do the same thing on robot 2, referencing robot 1. So that way they're both on the same page, that they both know to look out for each other. So while we were in there, we saw a combination check that was called a critical zone. Critical zones are great. They're a great automated way for the robots to work together using IIC. You'll start off by creating a fixture model. So menu, fixture model setups. In this example, we'll use an infinite plane. We teach the wall or the plane by teaching 3 points in the area where you wish to make the boundary. So here we have, this is our position data. Our position data for our plane. So the plane is out away from the robot 1,635 millimeters. So here's a visualization of the plane that we just, of this example's plane. So once we have the element set up, we can now define the combination checks. So we specify that we have robot 2 selected. We specify that there's a critical zone, and that critical zone is defined to look at itself. Now it's a little confusing, but okay. So we're using robot 2's teach pendant. I have robot hand. Basically, robot 2 is defined to look at robot 1. And then the critical zone is defined to look at itself. We'll press the detail button just as we did in the combination check setup for the wall, where we saw that there was a disabling input for the wall when the door was open. We'll press detail, and we're taken to the combination check critical zone details setup, at which point we can specify an input and an output. We also can specify the priority as far as which robot has priority to enter first. Okay, I just want to clarify that what these inputs and outputs mean. The robot input is basically, it's getting a signal that the space is occupied. So that's what the input is. The output is the robot sending a signal out saying that I'm in the space and I'm occupying it, letting other robots know that he's there. Again, the robot priority is who has control of it first. If they both request the zone within a certain amount of time, one robot is given priority. So after you you set that up, well then at this point, IIC critical zone it's defined and ready to use. If you want to simulate this in RoboGuide, make sure that you have your I/O interconnections established. So Robot 2 was low priority. We're going to watch an example where Robot 2 on the left is waiting for the critical zone for Robot 1 once Robot 1 clears. Go ahead and start this here. I have the 4D graphics display open to show you so that you can see you can visualize what the critical zone looks like. Robot 2 on the left. Robot 1 enters the zone. Once Robot 1 is out, Robot 2 knows he can go in. Now what's great about this critical zone is that if I go to the TeachPen editor to look at the programs, there are no additional instructions needed. Critical zones allow the robots to do this in an automated fashion, which makes your programming time a lot more pleasant. Yes, less headache. Yeah. Mike was just saying that you can make changes to your program and not necessarily have to worry about syncing or crashing errors because it's all automated. The robots do it for you. Going into wait condition. Wait condition is it's a great feature to have. I'll show you an example here of the wait condition, and this does use a TP instruction. It allows another layer of protection when it comes to waiting for doors to open or waiting for things to clear. So I'll go ahead and show you the example video here. Here is our work cell that we've been working with. I'm going to run through this program. I want to show you that this program, IIC main, we have an approach wait statement, an approach wait 1. So I'll go ahead and run this program. And the robot waited for the door to open even though there wasn't an explicit wait statement. See at the top of the screen we have a approach wait is enabled, wait 1. Now this wait 1 corresponds to setup, interference, waiting condition setup, waiting condition item number 1, which is wait 1, robot 1 with fixture 1 on robot 1. Again, robot 2 would never need to. I can go into the details and I can specify the digital input that satisfies the wait. Auto restart enabled, I can specify distances, how far from the fixture to wait. It's another tool in your IIC toolbox that will help to streamline your programming. Now in this check, going into the combination check, we have to make sure that this DI will disable the wall because, well, the wait condition will allow the robot to continue, but if the door isn't open, or what I should say is that digital input 8 isn't actually, if we allow it to go in, but we don't disable the combination check, then it's just going to stop the robot. So we need to make sure that not only is the wait condition satisfied, but then the combination check becomes disabled. Okay, so continuing on, we're going to go into deadlock prevention setup. Deadlock prevention is a great feature, especially when you're using multiple robots. When I say multiple, I should say more than two. Here are some examples of deadlocks. We have a bunch of robots that are going for the same work area, and A is waiting for D, D is waiting for C, C is waiting for A, or A is waiting for B, B is waiting for A, C and for D. So it's basically, it's a mess. These robots they're all trying to jump in there and work, but they're all waiting for each other to get out of the way before they can move, and it's a mess. And to be completely honest, programming something like this would seem like a nightmare as far as assigning zone priorities and knowing exactly where in the line in the teach-pendant program to enter the zone and when to exit the zone. So we've come up with deadlock prevention. Here's just a video of a before and after. Before deadlock prevention processing, these robots are working together, and we have a deadlock between two robots. Deadlock prevention runs through and it actually puts in zones for you in your TPU program. And it does the hard part for you. The figuring out how you're going to program it to work properly. So it automatically identifies interference areas. It performs analysis on your controller. If you make changes and you have to reanalyze, it's no big deal. Again, I said it automatically adds the enter and exit zones for you. And the great thing is that it really does completely eliminate the possibility of a deadlock. One of the issues, though, is that it does not support branching or conditional logic. Part of the way that this works is it scans through the program over and over and over again. And it creates actually, I'll go to the next slide here. It creates a blurb of every point in space that robot takes up. The interference regions are red. The displayed program workspace is green, and another robot program is displayed in blue. So it goes through and it finds every possible collision area. And if you have a conditional jump or conditional logic, well then you've got multiple different scenarios. You know, you've got multiple different point clouds, or I should say interference regions. So here is a quick example of how to set up the automatic deadlock prevention. If I were to set up deadlock prevention between these two robots, they both run the same program. It's called IIC main. Go into menu, setup, interference, into deadlock prevention setup. Now here we have schedules, and oh, I'm sorry, I accidentally jumped a slide. So here we have the schedules. but they're basically just like most FANUC schedules. They are a collection of data for a task. So we have a description. We can call it whatever we want. I'm going to go ahead and give it a name. Call it IIC deadlock or a demonstration. I'll go into the details. Here I have analysis on or off. I have a state, which is a read-only. Now here I'll set up the 2 robots, and I'll have to type in the program name. That the two programs that are going to be running at the same time. You type it in there. Okay, so robot 1, like I said, when I press cycle start, runs IIC main. Same with robot 2, IIC main. I'll go ahead and turn analysis on to start analyzing. Now have a look up here in the messages area, and you'll see that the IIC deadlock prevention analysis will post messages that it's working. Start the analysis, yes. It started mastering, and the analysis was completed. And it's as easy as that. Now, typically, you'll have a lot more points than my simple demonstration program, and it'll take quite a while longer. But it's a great tool. It's great to have, and it makes programming with multiple robots a lot easier. Now on to our next item, which is RailZone. RailZone is a tool specifically for robots that are on RTUs. They help to prevent collisions with rail robots. A lot of times when you're programming 2 robots on the same rail, it's very difficult to come up with a reliable method to keep the robots from hitting each other, especially if they're both servicing the same areas. So it really provides protections for rail robots. You can build models around the tooling and carriages, so that way that stuff's protected too. It supports the extended axis multi-group setup and top loader. Now, one thing I should note is, looking at the setup menu, you may notice that you didn't see I'm just going to back up a little here. You don't see a RailZone list in the setup. And, well, that's because this robot wasn't set up to be a rail robot. As soon as that RailZone gets activated as soon as the robot is set up for an RTU. I'll go back to where I was. Here is a video kind of how RailZone works, looking at the RailZone status and the messages on the top. We can see that it's working in an automated fashion. So let's run this here. Right robot zone cleared. The left robot is working. Right. Now it's waiting for right robot. So here it's just really a great way of protecting those rail robots. So it looks like we're running out of time here. Well, I guess just in time because we just reached the conclusion, and going through, we've covered the requirements, limitations. We've covered just about the bulk of it. Now, again, this webinar was not all of what IIC has to offer. There is more, and looking through the manual will really help you to figure out what to really help you figure out how IIC can help you. So in conclusion, it's a great tool. It'll help you to avoid collisions. It allows the robots to work in tighter areas, reduces your setup time, and really it's just you providing the robot the information it needs to do that. And with that, thank you all very much. And I think we are going to go ahead and open up the messages for questions here. So the question is, are there tools in RoboGuide for model setup similar to DCS? Yes. There is a yeah. At the moment, it's not as straightforward as DCS is with the with the tabs for, you type it in, you see a visualization instantly, and that. But there is a DCS copy function where you can design it with. Let me check the manual here. Oh, my mouse has disappeared. Oh, there it is. Do you have the manual handy? Yeah, I'm going to hand the headset over to Mike Webb here.
Okay, so within the copy, some of the tools, you can copy from DCS. So if you've defined your models in DCS, then you can copy those. They'll come over for the ride, so to speak. Also, if you had defined one robot with an object, say it's an end effector, and you have an adjacent robot that uses that same end effector, you can also copy from one robot to another, say via the IIC. You could say, okay, I want an object from robot 2 and from the IIC menu, and that can also be copied over. There's another tool, if you will, is if you have an object in an XML format, you can copy that from an XML file, and it'll bring it into the IIC. So hopefully that answers your tools for RoboGuide. Like say in RoboGuide, the best way I feel is how we did demonstrate is utilizing your 4D graphics, and whether you're on the floor with the actual robot or in RoboGuide, you can create your spheres or boxes and then view it in your 4D graphics. The next question is a great question. Critical zones separate. Are critical zones separate compared to or related to the enter zone and exit zones? So yeah, critical zones are they're isolated from deadlock prevention. That was the main question. Yeah, the enter zones and exit zones by deadlock prevention are isolated from any critical zones. So hopefully that answers that. Deadlock prevention is it's a tool in itself. Think of it that way. One of the things too, as far as deadlock prevention goes, it's analyzing that path as it stands. So if you made some process changes in that path, you would want to rerun your deadlock prevention analysis, and it'll update your zones accordingly. So if there's any other questions, we'll stand by. Otherwise, thank you very much for your time. Hope that you enjoyed our webinar.
Well, thank you very much, Mike and John. We hope you enjoyed today's webinar. If you do have any additional questions, we're going to have a slide at the very end here where you're welcome to send John an email, and he can try to answer the questions to the best of his ability. Just a reminder, next week we do have another webinar covering image pre-processing tools in IR Vision, and that's with Dave Deckel, a really excellent presenter. So we hope to see you then. I'd also like to remind you that this webinar series is one of the exclusive benefits of being part of our authorized integrator network. These are not available to anybody else outside of the network. And we also have a number of other benefits as well, including the FANUC Sales Toolbox, the Robotics Advantage Program, many marketing programs related to Google AdWords and other trade promotions, and also access to the CRC website. So once again, thank you very much for coming. It was a pleasure to have you here today. Have an excellent Friday, an excellent weekend. We'll leave the slide up for a few moments to take down the information if you so desire. We hope to see you next time. Thank you very much.